It was a pure adding machine coupled with a printer, a bell and a two-sided display that showed the paying party and the store owner, if he wanted to, the amount of money exchanged for the current transaction. The cash register was easy to use and, unlike genuine mechanical calculators, was needed and quickly adopted by a great number of businesses. 84 companies sold cash registers between 1888 and 1895. Only 3 survived for any length of time. 74, in 1890, 6 years after John Patterson started NCR Corporation, 20,000 machines had been sold by his company alone against a total of roughly 3,500 for all genuine calculators combined. 75. By 1900, NCR had built 200,000 cash registers. 76, and there were more companies manufacturing them, compared to the Thomas Forward/Pay an arithmometer company that had just sold around 3,300. 77, and Burroughs had only sold 1,400 machines. 78, prototypes and limited runs. The arithmometers built from 1820 to 1851 had a one-digit multiplier /divider cursor, ivory top, is on the left. Only prototypes of these machines were built. In 1820, Thomas de Colmar patented the arithmometer. It was a true 4-operation machine with a one-digit multiplier /divider. The Millionaire calculator released 70 years later had a similar user interface. 79. He spent the next 30 years and 300,000 francs developing his machine. 80. This design was replaced in 1851 by the simplified arithmometer, which was only an adding machine. From 1840, Didier Roth patented and built a few calculating machines, one of which was a direct descendant of Pascal's calculator. In 1842, Timoleon Morel invented the arithmoral, based on the arithmometer, which could multiply two numbers by simply entering their values into the machine. In 1845, Israel Abraham Stoffel first exhibited a machine that was able to add, subtract, divide, multiply and obtain a square root. Around 1854, André Michel Guéry invented the ordonnateur statistique, a cylindrical device designed to aid in summarizing the relations among data on moral variables, crime, suicide, etc. 81. In 1872, Frank S. Baldwin in the U.S. invented a pinwheel calculator. In 1877, George B. Grant of Boston, Ma., began producing the Grant mechanical calculating machine capable of addition, subtraction, multiplication and division. 82. The machine measured 13 x 5 x 7 inches and contained 80 working pieces made of brass and tempered steel. It was first introduced to the public at the 1876 Centennial Exposition in Philadelphia. 83. In 1883, Edmondson of the UK patented a circular stepped drum machine. 84. Detail of an early calculating machine invented by Diderot around 1840. This machine is a direct descendant of Pascal's calculator. Grant's barrel, 18771900S to 1970s. Mechanical calculators reached their zenith. Two different classes of mechanisms had become established by this time, reciprocating and rotary. The former type of mechanism was operated typically by a limited travel hand crank. Some internal detailed operations took place on the pull, and others on the release part of a complete cycle. The illustrated 1914 machine is this type. The crank is vertical, on its right side. Later on, some of these mechanisms were operated by electric motors and reduction bearing that operated a crank and connecting rod to convert rotary motion to reciprocating. The latter type, rotary, had at least one main shaft that made one, or more, continuous revolution, one addition or subtraction per turn. Numerous designs, notably European calculators, had hand cranks and locks to ensure that the cranks were returned to exact positions once a turn was complete. The first half of the 20th century saw the gradual development of the mechanical calculator mechanism. Mechanical calculator from 1914, an adiator camp used for addition and subtraction. The Dalton adding listing machine introduced in 1902 was the first of its type to use only 10 keys, and became the first of many different models of 10-key add listers manufactured by many companies. In 1948 the cylindrical Curter calculator, which was compact enough to be held in one hand, was introduced after being developed by Kurt Stark in 1938. This was an extreme development of the stepped gear calculating mechanism. It subtracted by adding complements. Between the teeth for addition were teeth for subtraction. From the early 1900s through the 1960s, mechanical calculators dominated the desktop computing market. Major suppliers in the USA included Friden, Monroe, and SCM/Marchant. These devices were motor-driven, and had movable carriages where results of calculations were displayed by dials. Nearly all keyboards were full. Each digit that could be entered had its own column of 9 keys, 1-9, plus a column clear key, permitting entry of several digits at once. See the illustration below of a Marchant Figmatic. One could call this parallel entry, by way of contrast with 10-key serial entry that was commonplace in mechanical adding machines, and is now universal in electronic calculators. Nearly all Friden calculators, as well as some rotary, German, dials had a 10-key auxiliary keyboard for entering the multiplier or undoing multiplication. Full keyboards generally had 10 columns, although some lower-cost machines had 8. Most machines made by the 3 companies mentioned did not print their results, although other companies, such as Olivetti, did make printing calculators. In these machines, addition and subtraction were performed in a single operation, as on a conventional adding machine, but multiplication and division were accomplished by repeated mechanical additions and subtractions. Friden made a calculator that also provided square roots, basically by doing division, but with added mechanism that automatically increment the number in the keyboard in a systematic fashion. The last of the mechanical calculators were likely to have shortcut multiplication, and some 10-key serial entry types had decimal point keys. However, decimal point keys required significant internal added complexity, and were offered only in the last designs to be made. Handheld mechanical calculators such as the 1948 Curter continued to be used until they were displaced by electronic calculators in the 1970s. Triumphator CRN1, 1958, Walther WSR160, one of the most common calculators in Central Europe, 1960, Dalton adding machine, CA 1930, mechanism of mechanical calculator Mercedes Euclidische, mod. 29 at the Museum Europäischer Kulturen. Typical European 4-operation machines use the Ardner mechanism, or variations of it. This kind of machine included the original Ardner, Brunsviga and several following imitators, starting from Triumphator, Thales, Walther, Facit up to Toshiba. Although most of these were operated by hand cranks, there were motor-driven versions. Harman calculators externally resembled pinwheel machines, but the setting lever positioned a cam that disengaged a drive pull when the dial had moved far enough. Although Dalton introduced in 1902 first 10-key printing adding, 2 operations, the other being subtraction, machine, these features were not present in computing 4 operations machines for many decades. Facit 1932, was the first 10-key computing machine sold in large numbers. Olivetti Divisuma 14, 1948, was the first computing machine with both printer and a 10-key keyboard. Full keyboard machines, including motor-driven ones, were also built until the 1960s. Among the major manufacturers were Mercedes Euclid, Archimedes, and MADAS in Europe. In the USA, Friden, Marchant, and Monroe were the principal makers of rotary calculators with carriages. Reciprocating calculators, most of which were adding machines, many with integral printers, were made by Remington Rand and Burroughs, among others. All of these were keyset. Felt and Tarrant made comptometers, as well as Victor, which were key-driven. The basic mechanism of the Friden and Monroe was a modified Leibniz wheel, better known, perhaps informally, in the USA as a stepped drum or stepped Drekiner. The Friden had an elementary reversing drive between the body of the machine and the accumulator dials, so its main shaft always rotated in the same direction. The Swiss Maders was similar. The Monroe, however, reversed direction of its main shaft to subtract. The earliest Marchants were pinwheel machines, but most of them were remarkably sophisticated rotary types. They ran at 1,300 addition cycles per minute if, plus, bar is held down. Others were limited to 600 cycles per minute. Because their accumulator dials started and stopped for every cycle, Marchant dials moved at a steady and proportional speed for continuing cycles. Most Marchants had a row of 9 keys on the extreme right, as shown in the photo of the Figmatic. These simply made the machine add for the number of cycles corresponding to the number on the key, and then shifted the carriage one place. Even 9 add cycles took only a short time. In a Marchant, near the beginning of a cycle, the accumulator dials moved downward into the dip, away from the openings in the cover. They engaged driver gears in the body of the machine, which rotated them at speeds proportional to the digit being fed to them, with added movement, reduced 10-1, from carriers created by dials to their right. At the completion of the cycle, the dials would be misaligned like the pointers in a traditional watt-hour meter. However, as they came up out of the dip, a constant lead disc cam realigned them by way of a limited travel spur gear differential. As well, carries for lower orders were added in by another planetary differential. The machine shown has 39 differentials in its 20-digit accumulator. In any mechanical calculator, in effect, a gear sector or some similar device moves the accumulator by the number of gear teeth that corresponds to the digit being added or subtracted. 3 teeth changes the position by a count of 3. The great majority of basic calculator mechanisms move the accumulator by starting, then moving at a constant speed, and stopping. In particular, stopping is critical, because to obtain fast operation, the accumulator needs to move quickly. Variants of Geneva drives typically block overshoot, which, of course, would create wrong results. However, 2 different basic mechanisms, the Mercedes Euclid and the Marchant, move the dials at speeds corresponding to the digit being added or subtracted. A1 moves the accumulator the slowest, and A9 the fastest. In the Mercedes Euclid, a long slotted lever, pivoted at one end, moves 9 racks, straight gears, endwise by distances proportional to their distance from the lever's pivot. Each rack has a drive pin that is moved by the slot. The rack for 1 is closest to the pivot, of course. For each keyboard digit, a sliding selector gear, much like that in the Leibniz wheel, engages the rack that corresponds to the digit entered. Of course, the accumulator changes either on the forward or reverse stroke, but not both. This mechanism is notably simple and relatively easy to manufacture. The Marchant, however, has, for every one of its 10 columns of keys, a 9-ratio pre-selector transmission with its output spur gear at the top of the machine's body. That gear engages the accumulator gearing. When one tries to work out the numbers of teeth in such a transmission, A straightforward approach leads one to consider a mechanism like that in mechanical gasoline pump registers, used to indicate the total price. However, this mechanism is seriously bulky, and utterly impractical for a calculator. 90 tooth gears are likely to be found in the gas pump. Practical gears in the computing parts of a calculator cannot have 90 teeth. They would be either too big, or too delicate. Given that 9 ratios per column implies significant complexity, a marchant contains a few hundred individual gears in all, many in its accumulator. Basically, the accumulator dial has to rotate 36 degrees, 1/10 of a turn, for 1, and 324 degrees, 9/10 of a turn, for 9, not allowing for incoming carries. At some point in the gearing, one tooth needs to pass for a 1, and 9 teeth for a 9. There is no way to develop the needed movement from a drive shaft that rotates on ear evolution per cycle with few gears having practical, relatively small, numbers of teeth. The marchant, therefore, has 3 drive shafts to feed the little transmissions. For one cycle, they rotate a half, a quarter, and 1/12 of a revolution. 1. The 1/2 turn shaft carries, for each column, gears with 12, 14, 16, and 18 teeth, corresponding to digits 6, 7, 8, and 9. The 1/4 turn shaft carries, also, each column, gears with 12, 16, and 20 teeth, for 3, 4, and 5. Digits 1 and 2 are handled by 12 and 24 tooth gears on the 1/12 revolution shaft. Practical design places the 12th thread shaft more distant, so the 1/4 turn shaft carries freely rotating 24 and 12 tooth idler gears. For subtraction, the drive shaft's reversed direction. In the early part of the cycle, one of 5 pendants moves off center to engage the appropriate drive gear for the selected digit. Some machines had as many as 20 columns in their full keyboards. The monster in this field was the duodecillion made by Burroughs for exhibit purposes. For sterling currency, £/s/d, and even farthings, there were variations of the basic mechanisms, in particular with different numbers of gear teeth and accumulator dial positions. To accommodate shillings and pence, extra columns were added for the tens digit, s, 10 and 24 shillings, and 10 for pence. Of course, these functioned as radix 20 and radix 12 mechanisms. A variant of the marchant, called the binary octal marchant, was a radix 8 octal machine. It was sold to check very early vacuum tube, valve, binary computers for accuracy. Back then, the mechanical calculator...
Yes, break. The power is low. Yes, that was kind of interesting. But there's a lot of text and I start to get tired. It's 6 p.m. And I will start to upload this and I will find some more. I'll try to find just calculator, then cash register. Then I will find this Pascal, who's invented this first calculator. But I will do that without camcorder. But we are kind of out of time. But I need to get something to drink. The video will split in 30 seconds. Yes, so I will start upload this and charging, but the camcorder is it's down. But the video splits in a few 20 seconds, so we have 20 seconds. My video with Agabus is ready to go public, but I will continue